Hello, this is part 1 of the graphical solution method. We're going to be working on problem 1. It is a minimization problem with 3 constraints in addition to the non-negativity constraints. And the first question is to determine graphically the feasible region. Now I would have preferred to show you how to do this manually, but it's unfortunately not possible. So we're going to be using Excel. So to represent the feasible region, we first need to draw the lines representing each of our constraints. And the first thing we're going to do is turn these inequations into equations. So instead of x minus 2y is greater than or equal to 2, we're going to have x minus 2y equal to 2. So to represent this equation, we're going to have to represent this constraint, we're going to have to find a couple of points that satisfy this equation. For constraint 1, we can simply replace x by 0 and deduce the value of y. So if x is 0, y is going to be minus 1. It's simply going to be 2 divided by minus 2, so minus 1. We can do the same for the second point. We can just replace y by 0, but I'm gonna go ahead and use a different point since it's gonna look a bit neater on my graph. So I'm gonna be using the point of coordinates 8, 3. Let's see if it satisfies the equation. So 8 minus 2 multiplied by 3 is 8 minus 6 equal to 2. So the equation is satisfied. Okay, for the second constraint, we replace x by 0 in this equation, and y is 6. We do the opposite. We replace y by 0, and x is gonna be 6 divided by 2, which is 3. For the third constraint, I'm going to be using these 2 points just for the sake of convenience. You can choose any other 2 points that satisfy the equation. So 0 minus 4 and 3, 5. So these are our constraints. The lines represent our constraints, but we still cannot determine where the feasible region is. It could be this one, it could be this one, this one. The one thing we know actually is that it's supposed to be above this line, so it cannot be this one. It cannot be this one since we have a non-negativity constraints. Okay, so to determine where the feasible region falls, we're gonna have to determine which are the areas limited by each of the constraints. So for the first and third constraints, we have greater than or equal signs. So the areas they're limiting are facing away from the origin. They're going to be facing the right hand side, this area. For C1, it's going to be limiting this area, this whole area. Okay, so for third constraint, it's gonna be the same. It's gonna be facing the same way as the first constraint. It's gonna be facing this area here. Okay, so for the second constraint, however, it is a less than or equal constraint, so it's gonna be facing the area heading towards the origin, so it's gonna be facing the left hand side, this area. So the intersection of the areas limited by each of these constraints is actually this area. So this is our feasible region. Okay, so we have determined our feasible region as we have been instructed by the first question. Next question is to determine all basic feasible solutions. So what are the basic feasible solutions? They are the coordinates of the corner points of the feasible region. So there are this point, the coordinates of this point, and this point. So we can very easily determine the coordinates of this point and this point. This is obviously a point of coordinates 2, 0, and this one is of coordinates 3, 0. However, for this point, which is the intersection between C2 and C1, we're gonna have to solve a system of equations to determine its coordinates. So this is the system we're going to be solving. This is the equation of representing the second constraint, and this one representing the first constraint. We're going to be solving the system using the elimination method. So we multiply this equation by 2, and then we subtract the second equation from the first one. So we get 5y equal to 2 as the 2x minus 2x is equal to 0. Okay, and we reuse the second equation from the previous system. Okay, so 5y equal to 2, this means that y is equal to 2 divided by 5, and we plug in that value in the second equation. We get that y equal to 2 over 5 and x is equal to 14 over 5, or 0.4 and 2.8. So the third feasible solution is 2.804. We get back to our graph and try to pinpoint our basic feasible solutions. So point A is of coordinates 2, 0. This is point A. Point B is 3, 0. And point C is this one that we just found its coordinates. So it's 2.8, 0.4. So we have our basic feasible solutions, A, B, and C. So the third question is to find the optimal solution of the LP using the corner points method. The corner points method is simply plugging in the coordinates of the basic feasible solutions, or the coordinates of the corner points, and choosing the best solution. This is a minimization problem, so we are going to be choosing the smallest value. So we plug in the coordinates of each point in the objective function. Coordinates of A are 2, 0, so this is the objective function, so the objective value is equal to 2 multiplied by -6 plus 3 times 0. It's -12. For point B, it's -6 multiplied by 3, and the y is 0, so no need to add it, so -18. For point C, it's equal to 2.8 multiplied by -6 plus 3 multiplied by 0.4. And of course, the smallest of these objective values is this one, -18. So the optimal solution is the second basic feasible solution, represented by point B. So we have answered the third question. Our optimal solution is x equal to 3, y equal to 0, and the objective value is -18.